Dr. Dongkun Shen. Welcome to my series of instructional video. In this lesson, I'll show you how my sorting method sorts 9 words. There are papers that I wrote when I discovered this sorting method on July 3rd, 1998. But this video will help you more because it is designed for people with no academic experience in computer field. I'll try to explain my sorting method in layman's terms so that although you have no computer science background, this lesson will give you a good idea about how my sorting method sorts data. If you program a computer commanding it to do work, the computer will exactly do it as you request. The program is a series of mathematically correct commands. As long as you clearly command the computer what to do with the program, it will do the work. Therefore, I'll set up some mathematically correct commands as a promise, and we go step by step, keeping the promise, just like computer does. While my sorting method sorts these 9 keys, we'll understand how my method is defined and programmed. I'll draw or modify a graph on the whiteboard with some insertion of a key. Computerized view graphs in this video will show you each insertion process. One thing good about the video lecture is that students can always pause or replay the video to watch figures on the screen carefully, taking more time. I hope my students will do that for better understanding.
Shin Sort creates a tree with nodes. The key Kim will be read and the tree is created. Each node for each character is linked to another through a memory address in its left son's memory space.
Yeah, we have 9 words on the whiteboard. They are input. The first input is Kim, K-I-M. The Kim is read, and the Shin tree will be created. K-I-M. They are linked together. Each node represents a chunk of main memory space. Each node has space for its left son's memory address and right son's memory address. The computer system finds available memory space for each node whenever the program requests the main memory space for a node.
The internal data structure in main memory looks like the figure on the right side, but we draw a tree in a simplified way as shown in the figure on the left side. Just like in a father and son relationship, there is a link between a father node and his son node. Using the son's address that is stored in the father's node, one can go down from the father node to his son node. The first character K in the input Kim is compared with the root node's character K. They are the same. Then the computer logic moves down to left subtree or the left branch, because it is programmed that way to keep the definition of Shin sort. The second character I is compared with the character stored in the head node of the subtree. Both are the character I. They are equal. Again, by the definition, it moves down to left subtree. The third character, N, is compared with the node with the character M. Here the input character N is greater than the character M, so the Shin sort program goes down to right subtree this time, based on the address in the right son. However, the address indicates there's no subtree to be visited. The node for the character N is attached to node M by storing the memory address of node N in the right son's address of the node M. The fourth input character G is attached to node N through the N node's left son's address.
My method stores each character in an input string in a node and links them together using each node's pointer address for its left son. Here you see the linked nodes for the key Kim. The second input is King. We need to insert the second key. If a part of the current input string has been already stored in the created tree, it uses the relevant portion of the tree, which is Ki. K and I. In this Shin tree, we store 2 keys, Kim and King. The 2 keys share a relevant portion, the Ki nodes in the tree. The K node, I nodes are commonly used nodes for the 2 keys, Kim and King. So the common nodes, K and I, are shared for the 2 keys, Kim and King.
The tree is changed from the left side one to the right side one for a new key after the input king is inserted. Now, the right Shin tree has two keys, Kim and King. The total number of nodes is only 5, while the total number of letters for the two keys is 7. The node K and the node I are shared by the two keys. In the Shin tree, any starting sequence of letter nodes that is used for the key will be used again for other keys with the same starting sequence. The configuration of the main memory is shown again for the tree with two keys. 5 spots in the main memory are taken to give storage spaces for the 5 nodes. Memory allocation is provided not by the programmer, but by the operating system of a computer. Please pay attention to right sense or left sense address that points to different spot for the sense node. The first character L in the third input line is greater than K in the root node at the top. So the L node will be the right son of the K root node. All the following nodes will be attached through the left son from the L node for the key lion. Thus the left side tree has been changed like a tree in the right side after input lion is inserted. From now on, the main memory configuration will not be shown because of its complexity. The comparison will start with the root node, which is a K node at the top. The first character in the input kind is K, so it is the same with the root node. If they are the same, the next step is to go down to the left subtree using the left son's address. The left son node has I for its character, and it is the same with the second character of the input kind. The comparison shows that both nodes' character values are equal. Therefore, again it will go down to the left subtree using the left son's address of the I node. The left son's character M will be compared with the third character N in the input kind. The character value N is greater than the value M, so it will go down to the right subtree using the right son's address. Then the right son's node has character N, which is identical with the third character N in the input kind. Thus, it will go down to the left subtree to compare the fourth character D with the left son's node in the tree. Now, you see that by the definition of Shin sort, based on the result of each comparison, the direction go down to the left son or right son is determined. There are 3 kinds of results: same, greater, and smaller. First, if the comparison shows that both characters are the same, it goes down to the left subtree using the tree node's left son's address. Second, if the input character is greater than the tree's node, it will go down to the right subtree using the tree node's right son. Third, if the input character is smaller than the tree's node, then the input character's node should be inserted before the tree's node. Now, you see that how it moves based on the result of each comparison. The node has character G, which is greater than the character D, so the D node should be inserted before the G node.
My sorting method uses a pre-stored portion kin for the string kind. Because the input character D is smaller than character G, the D node will be inserted before the G node. You see here, this will copy the address that's stored in the left son's memory address in the node N, and then this pointer will point this one, and automatically it will be erased. Here in this branch of the Shin tree, the nodes for kin, K-I-N, usually become the common nodes for the keys kind, K-I-N-D, and K-I-N-G, king.
The figures show that kind is inserted without creating nodes for kin, K-I-N. It recognizes the pre-stored portion kin for the insertion. Only the node for the last character D is created and inserted just before the node G. We compare the first character J with the root node K at the top of the tree. The J node becomes the root node at the top because the character's internal value is smaller than that of the character K in the tree's current root node. Actually, the process is an insertion of a word jade at the top. The left side tree will be changed to the tree at the right side after the input jade is inserted. The root is changed since the letter J is the smallest among the first characters. In the Shin tree, the root node has the character j. The first input character k is greater than the root node's character j. By the definition of Shin sort, the program goes down to right subtree using the right son's address in the root j node. The first input character k is the same with the character of the right son, so it will move down to the left subtree. The second input character I is identical to the left son's character I in the tree. Because they are the same, the definition of the Shin tree will lead the program to the left subtree again. Since the third input character n is greater than the left son's character m, the program will move down to right subtree by the definition. The right son's character n is the same with the third input character n, so the sixth input kin is considered to be stored already in the tree. In this case, the terminal node n for the input kin is incremented by 1 to make a note of the duplication.
The sixth input, kin, is read to be inserted into the tree. Both kind and king have the string kin for their common nodes, kin. So string portion already has been stored. Therefore, the method has a record to remember the new input is the same as the existing string portion. To remember it, Shin sort increments the counter of the terminal node n, for there is an input string kin. The counter of the node n is incremented to be 1 from its initial value 0.
The string portion kin, kin, already has been stored in the tree, so the size of the tree will not be increased for the insertion. As the figure shows, only the counter in the n node is incremented from its initial value 0 to the incremented value 1. The seventh input cant is read. The first input character k is greater than the root node j, so we go down through the j node's right son. Then the node k is found, so we go down to his left son. The characters e and I compared instead of the whole strings. The input string cant is inserted right before kim because e is smaller than I. The right son of the e node will point to the I node to let the rest of the branch be connected to the tree. Although we have changed much in this tree whenever we have inserted the key, this tree is still a Shin tree because we abide by the definition of the Shin tree for the computer to operate in recognition of the already sorted keys. After cant is inserted, the left side tree is changed to the right side tree. The input strings part E and T is inserted just before the node I because the second character E is smaller than I. The eighth input cow is read to be inserted. The first character K in the word cow is compared with the character J in the root node. Since the character value of K is greater than J, the program lets the flow go down to the right subtree. The right son of the root node contains character K, which is equal to the first input character. If they are equal, it moves down to the left subtree by the definition. The next character in the input is I, and it is greater than the character E in the compared node in the tree. If it is greater, the program will move down to right subtree. The character I in the first node of the subtree is the same with the second character of the input word Kyle. Since both characters are the same, it will move down to the left subtree. The third character L in the word Kyle will be compared with the character M in the header node of the left subtree. Because the internal value of the character L is smaller than the value of M, the L node of the input word will be inserted in place of the M node. The right son of the L node will point to the M node, and the last character E in the input Kyle will be stored in the node that is attached to the inserted node L node through the L node's right son's address. This figure shows where the input Kyle is located in the tree on the right side. The program uses the pre-stored portion Ki in the tree, and it creates only two other nodes, L and E, and inserts them into the tree in order. The last input string Queen is read to be inserted into the tree. The first input character Q will be compared to the character J in the root node of the tree. Since Q is greater than J, the computer will move down to the right subtree of the root node. The first character Q is still greater than character K in the head node of the subtree. So the Shin sort program will move down to right subtree with the right son's address. The header node of the subtree has L for its character. The character Q is still greater than character L. The program will use the right son's address in the L node to go further down. However, there is no more right subtree after the L node. The program will let the right son of the L node to keep the address of the Q nodes, so that nodes of the input Quin can be attached to the tree. The figure shows how the left subtree has been changed to the right one after the input string Quin has been inserted. The character Q has the greatest internal value among the first characters of stored input strings. Thus, the rightmost place will be its place in the tree.
Here I want to show you how we search a key through the Shin tree. The example is here kind. This key will be searched, and we'll compare with header node with the first letter here K with the character in the root node, and K and J will be compared, and K is greater than J, so we'll move down to right subtree. And K are the same, so they are equal, so we'll move to left subtree. I and E will be compared. I is greater than E, we move to right subtree. Just like what we did in the insertion of key. If they are equal, then we move to left subtree. If the input key letter is greater, then we move to right subtree. If input key is smaller than the character in the node, then we move to left subtree. The same definition that is used in the search. So I and I are found. So I and I are equal. So we move to left subtree. N and L will be compared, and N is greater than L, so we move to right subtree because this is greater than L. And N and M are compared, and N is greater than M, so we'll move to the right subtree. So N is equal to this N here, so we'll move to the left subtree. Now we move the pointer to the next one, and D will be compared, so they are equal. So the key kind is found in this Shin tree. This is only an example. Now you see that we move down to the Shin tree based on the result of comparison. So each step is decided by the comparison made by the letter in the input and the letter in the node.
Let's search another key string kindy, K-I-N-D-Y. The searching process is the same sequence of comparisons we have just gone through in searching for the key string kind, K-I-N-D. After he finds the string kind, it will move from the D node in the tree to its left son. It will look for the letter Y. However, the D node has no left son, so it cannot continue searching for the letter Y anymore. Therefore, the program will notify us that no such key kindy exists in the tree.
Here this is a Shin tree because I have made it grow by abiding by the definition of the Shin tree. Computers are 100% mathematical machines. So if you clearly keep the definition in a program, you can communicate with the computer and let it perform the sorting and searching. When you see the created Shin tree, you may vaguely see that the keys are sorted. From the left of the tree, you see Jade, J-A-D-E. This is the first key in the sorted order. Then Kent, K-E-N-T, is the second one. The letter K is shared with Kent, and next one Kyle. This letter shared by Kent, K-E-N-T, and Kyle, K-I-L-E. And the following branch of the tree will share the key portion, K-I, that had been stored previously. The keys that share the previous portion, K-I, are Kim, K-I-M, and K-I-N, K-I-N, kin, because of incremented counter 1. The rest of the tree's branch share the key portion kin, K-I-N. They are kind, K-I-N-D, and K-I-N-G, which is king. The keys such as lion and queen, L-I-O-N and Q-U-E-E-N, that do not share any key portion will be put in the sorted order respectively. Thank you for your effort in understanding how my sorting method sorts the keys.